Okay, so welcome everybody, and I especially want to welcome today Professor Vahid Sandoghdar, our speaker. He's a true expert in all things nano-optics, from quantum nano-optics, which we'll hear about today, all the way to nano-optical applications in biophysics. He did his undergraduate degree, actually, I think as a transfer student in the UC system at UC Davis. So that's a cool connection with Cal. And then he went on to do his PhD at Yale with Ed Hines and Serge Haroche. And then he followed Serge back to Paris at École Normale Supérieure in order to do his postdoc there. And then he founded the Nano-Optics Group in Constance, Germany, under Linek. And this is where Vahid both achieved very highly celebrated and extremely challenging single molecule imaging through optical absorption, and also where he developed interferometric scattering microscopy, the label-free ultrasensitive detection and tracking of small objects, which is now propagated to many groups and many incarnations, including my own. He moved to ETH Zurich for 10 years before moving to Erlangen, Germany in 2011. And since then, well, he's the director at the Max Planck Institute for the Science of Light. And he's also founded another Max Planck Center for Physics and Medicine there. And he's continued to both deepen and broaden his scope so long as there's some sort of ultra-sensitive component and it involves light-matter interactions of some sort. I'm personally very excited to host him here. He's a Miller professor who's joining us on campus for the months of April and May. And I'm sure he'd be happy to meet with scientists of all ages. And he has a number of upcoming seminars in addition to this one. So they all will be distinct, each from the other. The next one is going to be next Tuesday. It's a physical chemistry seminar, which is also, do you have a, it's, no, that one is next Tuesday. It's complicated. He's very engaged. So I don't remember the topic yet, but it'll be, I think it's also quantum optics. I can't remember what it is. And then originally he was supposed to give a nano seminar this Friday, and that's been postponed another month. And he'll give a seminar in MCB on April 19th. So hopefully you will be able to catch him at various seminars and also flag him down if you are interested to meet. He's really excited to learn all of the things that are going on here at Berkeley. That's in Latimer 120 at 4 p.m. on the 11th. Yes. Okay, but with that, it's time for us to learn from Vahid. Okay, so I'll hand things over to him.
So this works well? Yeah. Higher. A little bit of mechanics. All right. Still? Now? All right, good. Well, thank you very much, Naomi, for this very kind introduction, of course, for the invitation to visit the campus. And as Naomi said, I have the privilege of spending April and May in Berkeley, so I would really be very interested to learn as much from you in whatever area of science you are. So I was told in the letter of invitation for this colloquium that not only I should start softly and give a general introduction, but I should also include some personal notes or things that have to do with my scientific career path. I'm not going to overdo that, but I have included a few little things there. starting with a letter of rejection that I got from Berkeley in 1984. So I had to dig this up in my files. So I came to the United States as a 17-year-old at the end of '83, beginning of '84, and I started applying to universities, and I had no idea how the system works. So it turns out that the Berkeley campus was closed, and they said, you know, you can go somewhere else within the UC system if you want. And so that's how I applied to Davis, because they're in the core system and they have a different rhythm, and so I could get in, and then I just finished there. So I thought it was kind of a funny thing. It's almost 39 years ago, right? All right. Now, Naomi mentioned that we work in 2 different areas, and I'm going to tell you more things that have to do with the quantum optics side of our work, and that's where my background is. I'm going to say something about that a little more. But I'm particularly excited about the biophysics side, and again, if you might be curious about this, I invite you to the other talks that I'll be giving in the next few weeks. And there are also openings, so if you're really interested in any of these things, do feel free to contact me in both areas, particularly if you're looking for postdoc positions. So it was also mentioned that there's this new center, and so this has to do with the biophysics side of our work. In the physics colloquium, talking to especially young physicists, I would like to emphasize the importance of how much you could be contributing to life sciences with your physics understanding. And that's what this whole center is all about. This building will be ready next year, and will be basically filled by physicists and mathematicians in the middle of the university hospital. And the idea is that you really want to do life sciences and basic medical research, not patient care, but basic medical research as a physicist. So, and the way we do it is we actually kind of train you to be able to do that. So you don't need to understand biology or anything like that, but you will be able to contribute to that. And there are amazing, there's an amazing number of really open questions that makes this whole effort extremely exciting. So I'd like to start by acknowledging the people who are in the part of the group that have to do with the talk today. So these are people with permanent positions, staff scientists, and postdocs and PhD students. And as usual, I'll be talking about the works of many people who, in the meantime, moved on. As a kind of a also part of the personal note, this is the main paper from my PhD work. Just try to kind of set the stage for the topic that I'm going to be talking to you about, and also as a part of kind of, let's say, how painful and how long it takes to realize your dreams. So at the time when I was a PhD student, we were sending atoms in a vacuum chamber in the middle of 2 gold-plated glass substrates that were at a distance of only about a micron from each other, and over a distance of the order of a centimeter or so. And what we wanted to study was to do laser spectroscopy and understand how these Rydberg states are shifted depending on the distance between the atoms and the surface. And by doing that, we would learn about forces like the Casimir-Poulter forces or van der Waals forces that have to do with the interaction of an atom and a surface in the near field. Now, the one thing that here you will see in common with many of the work that we have done in the meantime is this small distance. So that's kind of where the nano-optics part comes in, where you or become interested in near-field type of interactions. But the other thing is that you have atoms that go through, and this is 1992. It's still very much in the early days of atomic physicists wanting to trap atoms and cool them and to try to get control over an ensemble of atoms. And generally, there were people who were interested in doing optical experiments on individual emitters. So again, atoms would be one choice, but there could be other optical emitters. Generally, you would have the problem that you have an ensemble, and of course, every time you have an ensemble, there's a kind of a Poisson or a statistical distribution of these things. And if you wanted to just kind of try to zoom onto one of these emitters, you would, for example, would have the problem that your optical resolution is not good enough because you can focus down to the diffraction limit, which would be a few hundred nanometers, and in that you would still have way too many atoms or emitters, so you can't see them individually. This is the mindset of the late 80s, early 90s. I'm trying to kind of take you back to see why you would want to do the kind of experiments that we've been doing for the past few decades. Physicists were cooling and trapping atoms, but they couldn't trap and manipulate individual atoms yet, around 1992. Okay, this came out just a few years later. But people who were doing tunneling microscopy, of course, they could already do this. Tunneling microscopy was invented in the early 80s, and by the 90s, people were doing scanning tunneling microscopes, for example, seeing individual atoms on the surface of a silicon wafer, or in fact, you could even do this at a video rate and literally see how individual atoms are jiggling around. So these are oxygen atoms on a ruthenium surface. So these things were doable by the end of 90s, but as an optics person, you wanted to be able to do the same type of thing using photons and not electrons. And to some extent, we were still struggling to replace electrons in many of the things by photons. So that's a little bit of the mindset. So I'm gonna do a little better contrast. Don't fall asleep. I will be watching you. One of the breakthroughs was to detect single molecules. So before people could see single quantum dots and color centers and things that are fashionable these days, it was the organic molecules that were seen as individual optical emitters. So here's your colleague Eric Betzik in the department had one of the first reports on using a scanning near-field microscope. You see that you try to funnel light through a very small hole so that you would only see individual molecules at a time, but you still had to prepare your sample in a very sparse way, and then you would just scan across these molecules that were sitting on the surface, and they would light up every time that they would be excited, because these are fluorescent molecules. The kind of molecule that is used in this type of experiment in the terms of a structure would look like that. To the physicist, maybe this is completely uninteresting, and maybe even to the chemists. But the point is that you look at this structure and you see that you have all kinds of different atoms. You don't just have carbon, but you have other atoms, and their bonds are somewhat adventurous. They could be all over the place. But they give light, and these are the types of molecules that are used in dye lasers and in fluorescence microscopy and all of that. In terms of the electronic structure, they have, or energy levels, they have a ground state and an excited state electronically, but then of course also they have vibrational levels. And this whole thing allows you to excite it with a high energy. There's a fast relaxation to the lowest vibrational level, and from there you get fluorescence. And the fact that your fluorescence is at a different wavelength allowed people to be able to filter the excitation light, which would give you otherwise a very large background. And that was kind of the key to detecting individual molecules. But this kind of object is actually a little more complicated, because there's also the triplet state, and when you have this intersystem crossing going to the triplet state, the system could become dark. And this leads, for example, to blinking. But more so, once you're in the triplet state or excited state, if there is some oxygen around or other types of atoms that might undergo photochemistry, your molecule bleaches. And this is probably what you all know, that molecules bleach. And that is basically true for the great majority of systems at room temperature. But at about the same time, in fact, even a few years earlier, there were important works done in the group of W.E. Murner, who was at the time also not very far from here, but at IBM. And they were looking at organic crystals that were doped with a whole bunch of organic molecules. And I tell you what kind of molecules these were. And so again, they're looking now at ensembles. They're not trying to get better resolution. These molecules are doped at much higher concentration than before. But in frequency space, they would see that, there is a certain reproducibility. They called that the fine structure. It has nothing to do with the normal fine structure, but it's to say that if you scan the laser across, you would see certain reproducible ups and downs. And this has to do, and especially if you look here, for example, two different scans, there is a certain clear correlation between these two. So this is not noise as you're doing this, but there is some kind of a structure in there. There is not just, broad line. And it turns out that it has to do with the fact that if you have a whole bunch of molecules in a crystal, you have inhomogeneous broadening and homogeneous broadening. And when you go down to very low temperatures, under 2 Kelvin in this case, each line, the homogeneous line width becomes very small, but the inhomogeneity remains. And so from some kind of a broad thing, you begin to see individual peaks. And this, so this is a kind of a situation. Imagine that you have a crystal, and but the crystal is never perfect, and every molecule that sees a slightly different environment, which means that there is a certain inhomogeneity in the frequency or in the transition. And so if you scan, now this is new data from our own lab as a kind of an example. If you scan across, so up here is wavelengths, here is frequency, then you would see that you would have a whole bunch of very sharp lines, and these lines are as sharp as only a few tens of megahertz. For those who don't work with megahertz, this is basically the same line width that you would get from a free sodium or rubidium type of atom in the gas phase. So although you're working in the solid state, your homogeneous line width is as narrow as it could be, and I'll say something about that in the next slide. So here's an example of the kind of thing that happens. This is the molecule that we have. Now this molecule basically only has carbon and passivated with hydrogen. So in the modern language, this is a piece of graphene that is very carefully cut out and then passivated with hydrogen. And this rigidity of the system makes it much more of a much better optical emitter than these other molecules that you would usually use in fluorescence microscopy. These are not used in fluorescence microscopy because they're usually not water soluble. So that's why they're not as commonly used. Now, you put that in a matrix, in an organic matrix made of other types of molecules, for example, anthracene. And so when you scan the frequency, this is the crystal of anthracene that you would see. You would see that different molecules pop up at different times. And every time, what you're doing is you're exciting this transition and looking at the fluorescence that comes to one of these vibrational levels. And that's redshifted, so you can detect it very nicely. So this was basically the workhorse of this type of high-resolution single molecule microscopy in the whole of the 90s and 2000s. So here's now just a kind of a summary of the type of things that you would do. These are the typical molecules that have been used. You see that they're all of this aromatic kind of hydrocarbons. But by putting these rings at different places, you basically shift the frequency. You can have these molecules almost anywhere from 400 nanometers to 780 or 800 nanometers. So in that way, you have it's a little bit like a particle in a box type of problem. And you can put them in different types of matrices. And each time, as I mentioned before, if you go to low enough temperatures, you get a line width that is really the Fourier limit of the lifetime of the excited state, of the radiative lifetime of the excited state. And the quantum efficiency in these molecules is also nearly, it's at any rate higher than 90%. It's always difficult to measure the quantum efficiency very precisely. And that makes them extremely good sources of single photons, extremely good optical sensors. And so we've been working with these for the past 2.5 decades. And the way I came across this was that during my postdoc, I was dreaming of doing these type of experiments that I told you before with single atoms, but the technology for manipulating single atoms was just not as developed as it is today. And of course, even today, it's painful to work with individual atoms because you can't keep a single same individual neutral atom for an hour or a day or two. We can work with the same individual molecule for 2 years if we want to. Because this is not going anywhere, it's just sitting there. And of course, the price you have to pay is that you go to a cryostat and work at something like 1.5 Kelvin. All right, now interestingly, and when we started these works, I have to say that, you know, physicists were very kind of stuck up, and they considered molecules to not be quantum systems. I don't know what they thought of them, but every time you mentioned the word molecule, they thought that's chemistry. In the meantime, there is a certain move from the AMO community to actually appreciate molecules. And I will come towards the end of my talk why molecules are actually really very interesting quantum systems, because they're just much more complex and they can have much more different functionalities. And there is really a revival of efforts where people try to synthesize new molecules with interesting optical functionalities. We have taken just molecules that were known. We are not chemists. We don't actually understand the chemistry of it very well. So we've been abusing these molecules as very good optical emitters. All right. Now, I told you that the way those experiments were all done by detecting fluorescence. And fluorescence is a very good procedure because you can work essentially on absolutely no background. And every time that, even if there are only 10 photons that are emitted, you can detect those 10 photons with very good efficiency. The problem with fluorescence detection is that the light that is emitted has absolutely no phase information, and there's no coherence, there's no memory of what kind of light was actually exciting it in terms of the coherence of light. And if you want to do quantum optical operations, of course, you want to kind of keep the whole of the wave function in terms of phase and amplitude. So phase becomes important. Now, especially if you want to now, and everything I know, I had this very slow start into single molecule type of work, but nowadays detecting single molecules and single emitters in any way has become kind of a routine thing. You might have come across this in your undergraduate kind of lab work where you can do an experiment like that, whereas 30 years ago, you know, you would publish a Nature paper with it. But the challenge now is to actually go to a network of emitters that are talking to each other via photons. And that means that I have one molecule and it emits a photon, and this photon is scattered by the second molecule, and this one actually learns something about the first one and does that in a very efficient way. And then from 2, you want to go to 3, 200 to 200, whatever. So you want to make this kind of a light matter type of new environment where your individual emitters, atoms or molecules, are actually seeing each other because they're coupled to a certain optical mode. And I'll be, so that's kind of the new challenge. And of course, scaling up becomes important, but on the way, doing this very efficiently becomes absolutely key, because when you cascade things, if you lose 5% every time, after a few steps, you're left with no efficiency whatsoever. All right, now we've So in terms of kind of understanding how to do coherent interactions and detection of molecules, but also do that very efficiently, we realized that it should actually be possible to do this in the simplest way imaginable. Well, let me go to this one first. If you look in your textbooks, the cross-section for the interaction of an optical beam and or light and a two-level system or an optical dipole or a point dipole is as large as 3 lambda squared divided by 2 pi, where lambda is the transition wavelength. So this is basically lambda squared divided by 2, which means that the optical cross-section for a single atom is huge. It has nothing to do with the size of the atom, of course, but it's huge in the sense that if you think in terms of the definition of a cross-section, all you have to do is you have to get the area to which your light is confined to be comparable to lambda squared divided by 2. And that's completely allowable or doable within the laws of classical electrodynamics. So one can focus very tightly, and in principle, you should be able to send one photon, and that photon should then be interacting with your single atom with 100% efficiency. So this is the kind of mindset that we had, and that seems like a kind of a hand-waving magical thing, that there must be something wrong to it, you would think. And there were calculations before that said that you would reach maximum 50% efficiency. So in this paper, we calculated this and showed that, yes, you can really reach 100% efficiency, but you have to understand that the interaction of light and this atom is going to be basically an interference effect. That is, your atom radiates the light, and if the radiation interferes destructively with the incident light, in transmission, you're going to have no light. And that means that all the light is going to be back reflected. So you can use a single atom as a perfect mirror for an incoming beam of light, but to do that, you have to make sure that you match the wavefronts of the incoming beam to the mode in which the atom radiates, and that's a dipolar mode. So if you could put your photon in a dipolar mode and send it onto an atom, then it should be 100% reflected. And this is basically the same thing as saying that you have to focus very tightly, because if you decompose a focused beam into its multimodes, then the dipole has the largest component. So that kind of the two ways of thinking come together. Anyhow, so this shows that you really can reach this 100% efficiency, and we wanted to do experiments on that. You had to focus very tightly, but if you go to a cryostat, focusing very tightly down to the diffraction limit becomes a little bit of a pain. You can't use a normal objective, which is a complex object from your microscope. But the solution is fairly simple. You basically replace oil as immersion medium by glass, and you make that a half-ball lens so that you don't get refraction at the edges. And then a simple lens together with this one would do the job. So we implemented this in the mid-2000s and could really show that by focusing light onto a sample which has a whole bunch of molecules, if you tune the frequency of the light to one of the molecules, you would get a clear dip in transmission. And this is really, if you had your eye would literally see that the light has become dimmer because there was one single molecule in front of it. And by exploiting this very efficient interaction, we've done a number of things that I'm not going to have time to talk to you about because they're kind of older now. But the take-home message is that this interaction really could be very efficient, and at the same time, you see that it is not 100%. So the question is, why is it not 100%? Well, it's not 100% because our molecule is not a two-level system. And if you, in fact, take any atom or anything else, you would see that because of multiplicities and all of that, you rarely have a two-level system. It's in fact very difficult to realize a real two-level system. So when we excite this molecule, it can have all these other radiation channels, and they act kind of like a loss. In our molecules, about 30% comes down, and about 70% goes the wrong way. And so there's a certain factor that comes in terms of the cross-section. But now we can take advantage of the kind of a toolbox of atomic physicists and quantum opticians that has developed over the 80s and 90s. And it's to say that I put this molecule now in a cavity, and by doing that, I can enhance this transition to the point that becomes a lot faster than these other transitions. So relatively speaking, the role of these guys becomes unimportant. And then I can go towards a two-level system again and reach that 100% efficiency. So that's kind of what we want to do. And of course, when you put a molecule or an emitter in a cavity, what you're doing is you're circulating light many times. And now you can think that in the cavity, you have another focused beam. And every time that the light goes by, there is a sigma over A probability of interaction. So here, if you have a certain beam waste and a certain finesse that tells you how many times you're going back and forth, the figure of merit becomes the finesse divided by the beam area. And if you were to rewrite this, you would see that that's the same thing as saying that it's Q over V, where Q is the quality factor of the cavity and V is the mode volume. And of course, this is something that is probably more familiar to anyone who has worried about the so-called Purcell effect that enhances transitions in a cavity. And if you were to, this is not working anymore. Yeah, finesse is basically given by, you can think the number of times that this goes back and forth divided by, I think, 2 pi. So let me, this guy is not working. It doesn't have a battery anymore. I just can do this. No, it's my computer that is locked. Why is that? Okay. There, now it's working. So basically what you want to do is you want to have a Q that is large and a V that is small, if possible, when you're now thinking of designing this cavity. And overall, you want this number to be as large as possible. But for practical reasons, it's actually better to make your Q not too large, because a large Q means small bandwidth. And remember that we're going to be doing all of this in a cryostat. So a little bit of kind of experimental physics details comes in from a technology point of view, that you want to have a high Q cavity that runs in a cryostat. Usually you think that a cryostat is actually a kind of a noisy environment. So you have to do a little bit of your technical homework to make sure that this is going to be good. I'm not going to go through the details of that, but you're welcome to ask me later. So basically what we do is we take one of these crystal flakes that I've shown you before. This would be only a few hundred nanometers thick. We put them on a flat, highly reflecting mirror, and then we want to bring another curved mirror from the other side. And the idea is now to make the radius of curvature as small as possible so that you can make the mode volume as small as possible by bringing it very close to the other mirror. So the way we do this is, so the flat mirror is kind of straightforward. You put your crystal on it. And for the curved mirror, we can take the end of something like an optical fiber or an AFM tip. And then you go to your clean room and you do focused ion beam milling. And you can make very nice mirrors here. And if you do this right, it can be extremely smooth. And then you send it to be coated so that they put a multi-layer of dielectrics on it so that it becomes highly reflecting. And then you can use positioners to bring this to make this distance as small as possible. But now you have the great advantage that you can also choose to move this laterally so that you can optimize the position of the emitter with respect to the mode so that you can optimize your coupling. So that's kind of the approach that we chose. And I'm just going to show you the final outcome. This is the kind of a resonance that you would get from the cavity by itself. So it's a typical kind of cavity resonance. You see that the width is of the order of a few gigahertz. Remember that the line width of a molecule is of the order of, let's say, 20, 30 megahertz. So this is much larger than that. And now you can tune your cavity to the resonance of the molecule, and you would see that the transmission drops completely. So because of one single molecule in the system, you have completely changed the transmission of this kind of macroscopic object. So in an intuitive picture, you can think that it was the index of that single molecule that changed or the presence of the molecule changed the overall index of the cavity right at that frequency, so that you no longer satisfy the resonance condition, so light doesn't get in, but gets completely reflected. Now, when you do that, because this interaction is now very efficient, that is really just every photon that comes has nearly 100% probability of interacting with this molecule, means that the molecule is also changing the phase of the incoming laser beam completely. Again, think of something like an index. If you have a certain index, light goes through that and its phase gets shifted. So here we're showing that we can change this shift by about 60 degrees. You can also use this whole system as a kind of a photon router in the sense that if we now send a laser beam, this laser beam, I make the laser beam weak, but then it's still a Poisson combination of different types of Fock states. So you have a Fock state, 1 photon, 2 photons, 3 photons, or no photons. But the 1 photon interacts very efficiently with the molecule. The 2 photon doesn't interact as efficiently because at some point 1 photon saturates the molecule and the second photon can get through, if you think about it that way. So by doing that, you could see that the light that comes out is very strongly bunched in the sense that you no longer have single photon components in it. You have more probably 2 or 3 photons coming at the same time. So you can now really begin to play with the quantum optical properties of this interaction. You've reached that level. But more importantly, what we've done is we've essentially turned a complex object into something much simpler, which can be this composite of the cavity and a single molecule, can be seen as an effective new 2-level atom. What we also showed was, and I'm not showing you the details, was to replace the laser light by the light coming from a single molecule, a second single molecule. So you know that a single quantum emitter can be used as a source of single photons, because every time you go to the excited state, you can only emit 1 photon at a time. So what we have done is we've taken 1 cryostat and used this as a source of single photons, in which you have a sample and you have a whole bunch of molecules, and you excite one of them and collect the light that is emitted by that molecule. But you know that the light that is emitted by that molecule is a single photon state. And you send that light through a fiber to a second lab where this other experiment that I've been talking about is taking place, and replace the whole laser system and send these single photons and couple a single photon to a single molecule with a very high probability. So technologically, it's to say that we're now at the point where we can do these experiments. Scaling up this is very difficult because this is heavy machinery. But the way to scale it up is to put everything on a chip and miniaturize this whole thing so that then you can cascade it and go further and further. yeah, so we've also reached the strong coupling regime, and you can use that for I'm going a little faster because I think I need to worry about my time. But when you get to this level, you can have very strong nonlinearities, and you can have single photon switches and all of that. But let me talk about the scaling up and the fact that you can now miniaturize everything on a chip. Instead of having a focused laser beam now, you have a waveguide. And if you put your light through a waveguide and you have one molecule sitting in its evanescent field, when the photon goes by, it interacts with this one molecule, and you would again see very notable extinction dips. But that interaction is still not very efficient as it was before, because the molecule is a multi-level system and all of that. So we have to do the cavity on a chip as well. And the thing that the latest thing that we have is the paper on arXiv is that we have, for example, a waveguide. These are grating couplers you can use to couple light in, and then the light goes out here. Here is a disc. It's a micro disc with a diameter of about 5-6 microns. So the light can couple here, go through a whispering gallery mode type of resonance, and then it can get out through the other waveguide that is coupled to it and come out here, for example. Because this resonator is very small, the free spectral range is very large. So you see that we have several nanometers or 10 nanometers of spacing between the different modes of the resonator. And if you zoom into that, then this is now the resonance of, this is one of those resonances of the resonator. But in this case, there is already a molecule that is coupled very well. And you see again that there is a dip because of the coupling of one single molecule to it. You also see a few other molecules that are at different frequencies coupling a little less efficiently to it. Now, we also have electrodes integrated onto this chip. And the electrodes are very useful for applying an electric field and therefore a Stark shift so that you can tune the resonance of the molecule. And this gives you tunability. Remember that if I want to couple two molecules to each other, they have to talk in a resonant way via a photon, but the two molecules usually don't come at the same frequency. So I have to choose one and then tune the frequency of the other one so that it can talk to it. And that's why we need these microelectrodes. In addition to that, we have an integrated interferometer because we want to understand the phase difference between, for example, two molecules that are sitting on this disk. And here's an example of the story of two molecules that are coupling. It turns out in this particular case, there's a molecule here. There's another molecule almost diametrically across it. And this molecule is giving something of the order of 50–60% dip. So it's coupling well, but not amazingly well. And this one too. And then the two of them are now coupling to the same mode. And they happen to interfere in a constructive way in one direction and in a destructive way in the other direction. And those are little details. I'm not going to go through that. So you see here that the Q of the finesse of the resonator that I'm showing you here is not as high as the one that I showed you before with the open cavity. Here we need to improve our fabrication a little bit further to get to the same ballpark. But you see now that basically we're putting all these different tools in the toolbox, and when you put everything together, we should soon be able to have very efficient coupling to single molecules, but also a way to couple two molecules or more to the same common mode, and therefore force them to actually see each other. All right. Now, this is the kind of work that we've done where we've used really just the optical transition of the molecule, that main transition. So really trying to force the molecule to behave like a two-level atom. But the molecule is actually a much more interesting object than a two-level atom because it has all these vibrational degrees of freedom. Now, in quantum optics and quantum technology, a lot of people have been trying to develop optomechanical systems. So you try to take a mechanical oscillator and miniaturize it and cool it down so that it behaves like a quantum mechanical oscillator. Now, if you take a molecule, this is a God-given quantum mechanical system in the sense that it has mechanical degrees of freedom, and it is quantized. So it's already made very small, and that's where the beauty of chemistry comes in, because you can make this in a bucket, and you don't have to go to the clean room every time and do things. So we're now thinking of molecules in the context of an optomechanical object, and we would like to take advantage of its mechanical degrees of freedom, which are intrinsically coupled very strongly to its optical degrees of freedom. And this is something that many of the other systems can't give you. The problem is that the mechanical degrees of freedom or the vibrational levels of molecules are not, in the gas phase, they're extremely well studied in some cases, but in the solid state, they're just very, very poorly studied. Usually, if you want to know, for example, the line widths or line positions of these lines, and I showed you in some other slide that they're something of the order of 150 different levels for the kind of molecule that we're using. You would use a grating spectrometer. You would send the light through a grating spectrometer, but the grating spectrometer has a limited resolution. So if you look at a grating spectrometer, this is the main optical transition that I told you, and otherwise you would have a whole bunch of other ones at different frequencies, but the resolution is given by the slit of the spectrometer, and that's usually not so much better than 10 gigahertz or so. So we developed this method to do high-resolution spectroscopy, and it's actually using the same principle as STED microscopy in the sense that you stimulate depletion via different transitions, and by doing this trick, you can use the line width of the laser as the line width that is relevant. You don't need to worry about the details, but I just want to show that we're making progress in terms of characterizing the different lines that are in these vibrational levels. And what we found, for example, is that there are some lines that are much narrower than was thought before. Before, the best was measured 20, 30 gigahertz or so. But we've seen already things that are of the order of 1 or 2 gigahertz. And it is possible that through a design of the molecule, you would get to certain lines that are, because of symmetry or different reasons, they're not as broad. Now, what's the reason for these lines to be broad? If you think of a molecule in vacuum, the ground state, the vibrational levels, if you go back to your Einstein A coefficient, the vibrational levels should live for a very, very long time because your omega is in the infrared range, and that means that your Einstein A coefficient is extremely small. And it's true that in the gas phase, these vibrational levels could live for a very long time, milliseconds or seconds. When you put that in a crystal, the coupling to the phonons and to the matrix changes this game completely to the level of picoseconds. So the challenge now is, how can I get this picosecond back up to millisecond? These are several orders of magnitude that we want to bridge. And what I'm going to now show you at the end is that you can do phonon engineering of your environment, trying to get these lifetimes to become much, much longer than they would come in the natural system. Let's not worry about this. So this is the system that we set. So this is the last thing I want to show you. What we've done is, this is now theoretical work. It hasn't been realized in the experiment yet. But imagine now that you have your crystal in which your molecule lives. Now, the crystal itself is a mechanical object and has acoustic modes, and, for example, modes like that. Your molecule also has vibrational degrees of freedom. And they're both pretty bad in terms of Q. They both decohere very, very fast and couple very nicely to a bath, and they would have lifetimes of the order of picosecond. But if you make your crystal very small, then you can get some help. And part of the reason is that when your molecule is in the crystal, it actually is coupled to the matrix in the sense that if you put a little bit of pressure and change the distance between the atoms in the crystal, of course, your molecule feels that. So there is a natural kind of mechanical coupling or strain coupling between the molecule and the crystal. And the coupling strength, if you go through that, and this is something that, you know, in mechanical engineering, it would be known, or material science, what's interesting is that at the end, this coupling strength behaves quite similarly to what you know from photons and cavity QED, in the sense that it goes as a square root of omega, the frequency, and of mode volume. So now you see that by reducing the mode volume, you can improve the coupling strength as before when we try to make very small cavities. In this theory work, we show that if you choose the size of your crystal to be of the order of, let's say, micron or a little less, and the height would be a few hundred nanometers, something that's completely within reach in the lab, then this coupling can become comparable to the line width of the optical transition. So that's already kind of getting us in the ballpark. But it's not good enough to have these long lifetimes. But what you can now do is bring the kind of the last weapon, and that's a phononic crystal, in the same way that people use photonic crystals to manipulate light by putting a certain band gap, for example. People have shown, for example, the group of Oscar Painter was one of the pioneers in this, that you can also make a crystal type of structure, an array of mechanical oscillators, and by designing this, you can open a band gap in the now acoustic domain. But when we talk about acoustic, we're talking about a few gigahertz in this regime. And the frequency that we had from the crystal that I showed you before would also be something in that range, which means that we, by putting this crystal, this little anthracene crystal on top of a phononic band gap, we can prevent it from decohering so that its vibrational lifetime goes from a picosecond more to the millisecond. And now that my molecule is also coupled to this matrix, I can use the optical transition of the molecule to couple to the acoustic mode of the crystal, of the whole crystal, and that is now in the millisecond. And it looks like we should be able to realize this with the existing kind of technologies, and that's kind of what we're working on probably the next few years. So this hopefully gives you a little bit of a flavor of what this type of research has been doing or where it's going. And with that, I stop and be happy to answer any questions if there are some. Yeah, I mean, we're kind of bypassing the actual vibrationals of the molecule by itself. So that might have been a little misleading. the way I presented it. The vibrational levels, I mean, that's in a way, if you think about the of the molecule as an optomechanical system, actually the advantage is that the levels are at terahertz and not gigahertz. So in that way, this is already a very tight system, and it has very large splittings. So if we could make one of the molecular levels long-lived, then we would be in an amazing regime. What we're doing here is we're saying, you know, the molecule is coupling to this crystal. Let's use the crystal as its wings, kind of mechanical wings, and we just use those modes. Yeah. Right, yeah. Yeah, no, thanks for asking. I didn't explain that so that you couldn't have understood it very well. So what we're doing is, remember that this was the main transition, the zero phonon line. That's the transition that is very narrow, like 20, 30 megahertz. But what we do now is we pump higher. That state comes down very quickly. And from this state, we stimulate a transition to this level. And now we're going to monitor the population of this state by looking at the fluorescence that comes to other states. So we have a certain level of fluorescence, and every time that we become resonant with one of these lines, we stimulate efficiently, and then we get a dip. And that happens, basically, you go through the intrinsic kind of line width of that transition, but your laser is not bothering you. Yep. Yeah, so it's not spin. In fact, that's one of the, let's say, handicaps of these molecules or advantages of the molecules. They're in a spin zero state, so they don't couple to spins, and the whole matrix is spin zero. So that's not the problem. These are phonons that couple, and for DBT, actually, you can go almost to 4 Kelvin. The other molecules happen at around 2 to 2.5. So there's nothing, I mean, it happens to be a coincidence that somewhere between 2 and 4 these things happen, but there's nothing fundamental about that number, of course. But so one of the reasons almost everyone nowadays works, or 2 reasons, works with DBT. One is that you can use a Ti-sapphire laser instead of a dye laser. So I grew up with dye lasers. I love them, but graduate students don't seem to appreciate this. And the other one is that you can work at much higher temperature. I mean, much higher. You don't have to go to pump on your helium, and you can work, for example, at 3 Kelvin, and you're totally good. Yeah. Yeah, that's also a very good question. I didn't say anything about that. I had this one slide that I skipped because I realized I was going slowly, where I showed the basics of it. So this is kind of explaining a little bit how we do that. Here there's no microdisc, but it is still an integrated kind of system in the same way. So what we have is we have a glass substrate, and on that we have this titanium dioxide circuitry, waveguide, disc, whatever. So the way we do it usually is that we make a counter substrate with a little bit of an indentation. This is only a few hundred nanometers. And then we suck the crystal in a molten phase into this, and then it crystallizes when it gets cold. So then what you have is a very thin layer of crystal on top of this circuit. And that crystal is doped with molecules. So some of them happen to be in the evanescent kind of range of your waveguide or micro-resonator. That's how we place them. So it's not, right now, it's not done in a controlled way, but you can have you can have fairly high doping so that you have a whole bunch of, so for example, you see here that in one waveguide, you have a whole bunch of molecules along the way. So statistically, you end up having a whole bunch. Let me show you one thing that we're also doing now is to do more of a systematic thing, and that's printing nanocrystals. So you can try to kind of form nanocrystals in a way at the location that you really want, and we are hoping that this allows us to actually place molecules where we want. So we you know, when you do this, there's a little bit of kind of study that you have to do. I mean, another thing that I didn't mention, but anyone who works in the solid state kind of high resolution spectroscopy knows that quite often there is dephasing, not dephasing, but there is spectral diffusion. So if your crystal is not perfect, then these lines can be narrow, but on the scale of 1/10 of a second to a minute, they might be wandering around because the crystal is breathing and something is changing inside and all of that. So you have to, when you do this nanocrystal, this could also happen. So we're kind of taking some time to understand how we do this so that the lines actually stay stable. And it looks like it's doable to do that. Yes, please. Well, thank you.
It looks like when you put a second molecule between the first molecule, you improve the system by half. Because the system becomes the 25. So does that imply n molecules to do that n times?
Yeah, that was a coincidence. That's not completely true. That yeah. So this here was yeah. This is actually kind of, there's a lot of little technical details involved here. So when you have this kind of a disk, it's a little bit of a tricky system because you have clockwise modes and counterclockwise modes, and that makes the situation different from a typical Fabry-Perot where you just have one direction that you go, right? And that means that when you have a perfect coupling, you're going to reach 25% in this regime and not 100%. So these molecules are actually not as far from perfection as it looks, because in the best case, they would come to 25%. Now, when you put them together, you see that it goes a little bit beyond 25%. And that's really the first indication that they're not just having a trivial kind of addition of photons, but they're actually beginning to interact with each other in a less of a trivial way.
But theoretically, would you expect each additional one to
No. So if you actually have a whole bunch, it becomes very yeah. These are interesting questions. Yeah. Let me show you. Yeah. So the if you put two and they're perfectly coupled with each other, then you expect to get a splitting. So they don't just add up. And as you put more and more, this splitting becomes more complex. I'm trying to find a slide and I don't have it. So if you put two and imagine that you have a single mode, and when your molecule or atom emits, its photon is bound to be in this mode. So this photon comes, and I showed you that if you can manage that, then the interaction is going to be basically 100%. So that means that you would have two atoms that are sitting in a waveguide at a very large distance, but they would know about each other. They are already coupling, if you want, via virtual photons. If you were to now probe this via spectroscopy, you would not see one resonance, although they are identical. You would see a little dip. And if you put more and more, this dip becomes deeper and deeper and becomes more and more complicated. So it's a little bit kind of has the flavor of super radiance, where you put a whole bunch of atoms next to each other, and then you end up having n2 levels. So you have lots of multiplicities that are allowed. Yeah. 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 So that's kind of the ideal kind of regime where we want to go. And the physics of it should be really exciting and interesting, because you're having this material properties that are usually local talking to each other via the optical channel, although they're not in contact with each other. Oh, there's a class, yes. I'll be around, all right. I'll send that to you.
Let's just thank Vahid once more.
You guys still have a class.